Today we dive into one of the most thrilling findings in planetary science, Perseverance rover's discovery of potential biosignatures in a Martian rock sample taken from Jezero Crater. Why should you keep watching? Because this could be the closest evidence yet that Mars once hosted life. We'll explain exactly what was found, those strange leopard spots, minerals like vivianite and greigite, how scientists got to these results using rover instruments, why these particular minerals are so compelling, and what the implications are for the search for life. By the end, you'll see what this could mean for Mars, for science, for all of us. In July 2024, Perseverance collected a core sample from a rock named Chiava Falls, located in the Bright Angel Formation in Jezero Crater. That sample, dubbed Sapphire Canyon, is key. What Perseverance's instruments found were rust-red mudstone bearing what looked like leopard spots and dark speckles ring-shaped and spot-like features embedded in the rock. Using its onboard instruments, the rover mapped chemical composition and structure at fine scale, identifying patterns of minerals including vivianite, iron phosphate, and greigite, iron sulfide. These rocks date from about 3.2 to 3.8 billion years ago, a time when Jezero was believed to be a lake basin fed by rivers. Because the rocks are made of fine-grained clay and silt, the surrounding sediment preserved organics and chemical conditions well, giving a chance for biosignatures to survive across eons. What makes the discovery especially exciting is the pattern. These minerals are arranged in reaction front zones where chemical gradients existed, with iron, sulfur, and phosphorus interacting alongside organic residues. That suggests chemical reactions were happening in ways that, on Earth, are often driven by microbes. But scientists are careful. Non-biological processes can sometimes mimic these signals. Still, the sample offers one of the strongest cases for preserved ancient activity we've seen on Mars. Vivianite and greigite are not arbitrary names. They carry weight in biology and geology. Vivianite, an iron phosphate, is commonly found in wet, low-oxygen sediments on Earth, places with decaying organic matter. Greigite, an iron sulfide, often appears in environments where microbes reduce sulfate, producing sulfide that then binds with iron. The point is, these minerals, when found together, especially in a pattern such as nodules, fronts, or spots, are strong candidates for biosignatures, features that suggest biological processes. On Mars, spotting organic carbon, sulfur, phosphorus, and oxidized iron together with these minerals raises the plausibility that microbial metabolism once played a role. Yet it's critical to keep perspective. Many abiotic, or non-living, processes can also produce vivianite and greigite under certain conditions such as high heat or acidity. But the Chiava Falls sample does not show evidence of such extremes, making it harder to explain without considering biology. This is why scientists are calling it a potential biosignature. It's not a smoking gun, but it is a compelling fingerprint that biology might have left behind. So why does it matter? Because if Mars really did produce these minerals in the same way Earth's microbes do, then we risk staring at one of the clearest hints yet that life is not unique to Earth. Even if the answer turns out to be geology, it still reshapes our understanding of how planets create complex chemistry under ancient conditions. Because this is such a strong candidate for a biosignature, the next steps focus on testing, not declaring victory. The only way to know for sure is to bring the sample back to Earth. In laboratories here, scientists can perform analyses far beyond what a rover can do. Isotopic measurements, molecular imaging, and high-resolution searches for chemical markers of life. NASA's Mars Sample Return mission will be critical for that, though its timeline stretches into the 2030s. In the meantime, scientists are running parallel studies to explore whether non-biological pathways could mimic the observed patterns. Could chemical reactions alone form vivianite and greigite in those specific arrangements under the calm, lakebed conditions at Jezero? Or is biology the simpler explanation? Laboratory experiments simulating Martian conditions will help narrow those possibilities. The implications are profound. If this is confirmed as biological, it would show Mars not only had habitable conditions, but may actually have hosted living microbes. That would be the first discovery of life beyond Earth, rewriting everything we thought we knew about biology, evolution, and the uniqueness of our planet. Even if it's geology, the result still expands our understanding of Mars's chemical complexity, showing us how far nature can go without life. For exoplanet research, it offers a roadmap. Water, fine sediments, and certain mineral combinations are prime places to search for life elsewhere. This moment is huge not because we've proven life on Mars, but because we're closer than ever. The discovery of vivianite and greigite, an ancient lakebed mudstone from Chiava Falls, is among the strongest evidence yet of a potential biosignature. What was once speculation now has concrete chemical and mineral clues. What we learn next through lab experiments, and, eventually, return samples will decide whether these are whispers of ancient microbes or an extraordinary geological trick. Either way, Mars is teaching us new rules about life in the universe. Thanks for watching, and don't forget to like, share, and subscribe. Your support keeps this journey going.